Good morning, my dear students in modern geometry. So as promised, I am now providing you with a supplement instructional video for you to understand our lessons better. So this time we shall start with lesson 1 of module 1. So here in this lesson, our intended learning outcomes would be for you to be able to prove or disprove consistency of finite geometries by constructing models, and to verify the independence of finite geometries again by constructing models and through logical arguments. So in this lesson, you were asked to do an activity. I hope you have done your activity or this activity, for this would guide you to understand what an axiomatic system means. Why? Because in this activity, you can observe that there are limitations, there are restrictions given, and that those are, you would have to make use of all three matchsticks in making your figures. So such limitation would be the initial fact. Okay, so that would be the initial true statements. And then your observations as to what common properties of the groups of figures that you were able to come up with would be the new contentions, the new conjectures. Okay, if you would be able to prove them, then that it will become theorems. So that is exactly the same concept of an axiomatic system. Okay, so for us to be able to fully understand what really is an axiomatic system, let us read our book. So we have here page 2 of our book, which talks about axiomatic systems. So again, the reason behind why set theory and logic was made prerequisite for this subject, because this would require our understanding of deductive reasoning. Okay, so deductive reasoning takes place in the context of an organized logical structure, which we call the axiomatic or the deductive system. Okay, so such system has components. So what are these components? There are 5 components of an axiomatic system. First, you have the undefined terms here. So undefined terms, these are terms which are included in the discussion but need not be defined. Why? Because if we are to define all terms, we just end up making a loop. Like for example, if we are asked to define what do we mean by parallel lines? So these are lines that do not intersect. If you are to define what is a line, so we say a line is a set of points extended in opposite directions. But then we made use of points, so we would have to define points. A point is, let's say, our geometric interpretation of a location, okay, and the like. Then we'll have to define what is a location. It would be a never-ending process of defining terms. So that is why there should be terms that all of us has an idea but need not be defined. Okay, so that is what we meant by undefined terms. And then we have the defined terms. So along the way, we would need to discuss, or we would need to mention terms which make use of our undefined terms. So we can define these terms making use of the undefined terms. So for example, again, we define parallel lines as lines that do not intersect. So take note that this definition of parallel lines makes use of the undefined terms lines and the notion of intersect. So first we would have to define when do two lines intersect. So maybe we can define two lines intersect if they have a common point or they have at least one common point. Okay. Next, we have the axioms. Okay. So not all statements in an axiomatic system can be proven. Meaning there should be first an initial fact, an initial truth, a baseline. So these are what we call the axioms or the postulates. So from the axioms or from the postulates, from these given facts, we can then derive new observations. Okay? And then if we are able to prove that such observations are true, it rises up the next level and be called theorems. But in proving such conjecture or observations are true, we make use of what we call the rules of inference of the system of logic. Okay, here, rules of inference of a system of logic. We call it Aristotelian. So, once these conjectures are proven to be true, then they are called theorems. This axiomatic system should possess several important properties. The first property is the property of consistency. So we define an axiomatic system to be consistent if there is no two axioms, an axiom and a theorem, or any two theorems that contradict each other. Meaning that the truth of one must not imply the fallacy of the other. Okay? But it doesn't mean that the truth of one should imply the truth of the other. That doesn't mean that way. It only that if one is true, then it should not follow that the others are false for the system to be consistent. So it should be clear that it is essential that an axiomatic system be consistent, since it is very important, because if a system is not consistent, meaning both statements and its negative can be proven, then the system is said to be worthless. Okay, so but if it is evident that each theorem can be true at the same time for a single model or a single case, then we can say that the system is consistent. So how do we verify whether or not a system is consistent? In verifying the consistency of a system, we make use of models. Models are an interpretation of an axiomatic system wherein undefined terms are converted into concepts, and then axioms are represented using this representation. So it is said to be consistent if the model shows that all axioms are true in a single model. Now, there are models which we consider absolutely consistent, or systems that are absolutely consistent and relatively consistent. When is a system absolutely consistent? If the model, or if a model obtained uses real-world interpretations, because there can be no contradictions in the real world. So if such model makes use of real-world interpretations and proven to be consistent, then we say that the axiomatic system is absolutely consistent. Now, if the consistency of a model depends on the consistency of another axiomatic system, meaning it can only be consistent if another model is consistent or another axiomatic system is consistent, meaning its consistency is conditional. It depends on the consistency of the other. We call it relatively consistent. It has relative consistency. Okay, now for an example, let us take the 4-point geometry. A 4-point geometry is an example of a finite geometry. By the way, to understand what an axiomatic system is, let us first forget all we know about geometry. That the notion of lines, the notion of points, the notion of planes. Let us first forget all that. There is nothing true yet. Just like when God created earth, or when God created the world, there is nothing. Then there was light. Okay, it's just like that. Forget everything first, then clear your mind. We would start from scratch. Okay, so an example, we have here the 4-point geometry. In the 4-point geometry, the undefined terms are point, line, and on or contained. So this would be the terms that we would use in our discussion of the 4-point geometry. Point, line, and on. First axiom, there exist exactly 4 points. Okay, so hence the name 4-point geometry. The first fact given is that there are exactly 4 points. The second axiom, 2 distinct points are on exactly 1 line. Okay, if we would rephrase that, it means that every pair of points are on exactly 1 line. Meaning, if there are 2 points, then there should be a line containing both of them. The third and the last axiom in the 4-point geometry is the statement saying each line is on exactly 2 points. Meaning, if there is a line, then there should be exactly 2 points on it. Okay? So, we would really have to understand each statement by heart so that we can use them later. Okay, so to prove its consistency, we would have to make a model wherein all axioms are true. Now, a model can be of any form for as long as it's clear. So, for example, here is an example of a model for the 4-point geometry. Here, we interpret points as the letters A, B, C, and D. And the lines be columns that contain the letters. Okay? So, on, when you say on, the line or the point is on the line, meaning such point or such letter is on that column. Okay? It is contained in that column. So, since a line contains exactly 2 points, meaning each column would have 2 letters. So we have here AB, AC, AD, BC, BD, and CD. So here is a model. Now to verify the consistency, we first have to verify the axioms. First axiom, there are exactly 4 points. So we see that such axiom is satisfied because we have exactly 4 points, A, B, C, and D. Second axiom tells us that every 2 points is on exactly 1 line, meaning each pair of points is contained in exactly 1 line. Therefore, each pair of letters should be in 1 column. So for pairs containing A, we have AB, AC, and AD. For pairs containing B, which not contains A because those are already counted, we have BC and BD. Then for lines, for columns containing C, which do not contain A and B, we have CD. There can be no other pair that be made, hence we have these lines. So we see that each pair is on exactly one column. There is no pair that is duplicated in other columns. So this model satisfies the second axiom. The next, for the third axiom, it states that every line contains exactly 2 points. So we see here that each column has exactly 2 letters on it. Meaning, all 3 axioms are satisfied by this model. Hence, all axioms are true. Not one contradicts the other. Hence, we can say that the 4-point geometry is consistent. Another model that can be made is somewhat visual or graphic. Okay? So we here define or interpret points as dots. Then name the dots as 1, 2, 3, and 4. Then the lines interpreted as segments connecting the dots. And then when we say on, the point is on the line, meaning the dot is an endpoint of the segment and vice versa. So here, the interpretation and then the illustration why we can say that the system is consistent. Here we have the figure. So we have the dots 1, 2, 3, and 4, and then here are the line segments connecting the dots. So we see that first axiom 1 is true because there are exactly 4 points. Second, each pair of points 1, 2, 1, 3, and 1, 4, 2, 2, 3, 2, 4, and 3, 4 are on exactly one line. Meaning there is only one line segment connecting each pair. Also, we see that each line segment has 2 dots on it. Meaning the third axiom is true. Hence, we can say that the 4-point geometry is again consistent. Next, we have the property of independence. So we define an axiom in an axiomatic system is said to be independent if it cannot be proved by the other axioms. So this property pertains to an axiom in the system. But if all axioms in the system are independent, then the whole system is said to be independent. Okay? Again, if an axiom cannot be proven by the other axioms, then it is said to be independent of the other axioms. Okay? That means its truth does not depend on the truth of the other. In other words, it could be false even if the other axioms are true. Therefore, to verify independence, we simply have to make a model in which each axiom is independent. Meaning, we show a model wherein first axiom is not true even if the others are true. Then, the second, a model showing that the second is not true even if the first and the third are true, and so on for the third axiom. So here we have a model. Here are the models that showing the independence of the 4-point geometry. So here we see the model showing that axiom 4p.1 is independent. the model wherein there are only 2 points. So axiom 1 is not true. But axioms 2 and 3 are true. Why? Because here, since there are only 2 points, there is only one pair, AB. And such pair is on a line. And then, axiom 3 is also true because there is only one line here and such line contains 2 points. Meaning, axioms 2 and 3 are true even if axiom 1 is false. Therefore, axiom 1, axiom 4P.1 is independent of the other 2 axioms. Next, we have here the model showing the independence of the second axiom of the 4-point geometry. So we see here that there are 4 points, A, B, C, and D, meaning axiom 1 is satisfied. Next, the lines are AB and CD. So each line contains exactly 2 points, hence axiom 3 is true. But then, we can see that there is no line containing the points B and C. Hence, the second axiom is not satisfied even if the first and the third are both satisfied in this model. So we say that axiom 4P.2 is independent of 4P.1 and 4P.3. Lastly, here is a model showing that the third axiom of the 4-point geometry is independent. So we see again that there are 4 points, A, B, C, and D. And then, the lines are given to be ABC, AD, BD, and CD. So we see that the first axiom is true because there are exactly 4 points. And then axiom 2, which states that every pair should be in exactly one line. What are those pairs? AB, it is contained in ABC. Then we have AC, it is also contained in ABC. Then we have the next pair AD, contained in AD. Next pair is BC, which is contained in ABC. Next pair is BD, contained in the line BD. And lastly, we have the pair CD, which is contained on the line CD, meaning each pair is contained on exactly one line. Therefore, axiom 4P.2 is true. But then, axiom 4P.3 has been contradicted because there is a line which contains 3 points. Axiom 4P.3 asserts that there should only be exactly 2 points on a line. Meaning, in this case, both axioms 1 and 2 are satisfied, but then axiom 3 is not satisfied. Therefore, axiom 4P.3 is independent of the other 2. Now, we see that all 3 axioms are independent. Therefore, we can say that the 4-point geometry is independent. Now, let us move on to the third property of an axiomatic system. It is the property of completeness. We define an axiomatic system is complete if every statement containing undefined and defined terms of the system can be proved valid or invalid. In other words, if it is not possible to add a new independent axiom to the system. Meaning to say, proving new observations does not require additional assumption or an additional axiom. Therefore, the axioms or the system is complete. Okay, generally, it is quite impossible to demonstrate the completeness of a system. Why? Because every model has to be examined. If one can show that each pair of models are basically the same to one another, that is, they are just isomorphic, then we can say that the system is complete. But that would again be almost impossible because some axiomatic systems have a large number of models. So what do we meant by isomorphic, or basically the same? Two models, alpha and beta, of an axiomatic system are said to be isomorphic if there is a one-to-one correspondence theta of phi from the set of points and lines of alpha onto the set of points and lines of beta that preserves all relations. Okay, in which case the relation being on. Therefore, there should be a one-to-one correspondence, meaning the number of points in one should be the same number of points in the second, and then the relation of being on is being preserved in the model. Meaning, if a point P is on a line L, then the image of P under phi should be on the image of L under phi. Okay, for example, so if we would go back to the two models of the 4-point geometry here. So we see that the two models are basically the same. Why? Because the points are just renamed from A, B, C, D. The points were just renamed as 1, 2, 3, 4. And then we see here that the line AB is just the line segment 1, 2 here. 1, 2. The line AC is the line segment 1, 3. The line AD is the line segment joining 1 and 4 and so on. Meaning, there was just a change of name, change in nomenclature. Therefore, the two models are basically the same. So, if we would assume that those are the only models that would represent the 4-point geometry, then we can say that the 4-point geometry is complete. Now, let us move on to theorems. Again, a theorem is a new observation other than the axioms that can be proven using the axioms in the system. So, an example of a theorem in the 4-point geometry states that there are exactly 6 lines in the 4-point geometry. There are exactly 6 lines. This is not given as an axiom but just a theorem because this can be proven using the axioms. Okay, let us try to construct the proof of such theorem. So we see here, I have rewritten the axioms of the 4-point geometry and the theorem that we are to prove. So the statement asserts that there are exactly 6 lines in the 4-point geometry. But then, again, axiom 1 states that there are 4 points. Axiom 2 states that every pair of points should be on exactly 1 line. Meaning, if we are to count the number of lines, we would have to count the number of pairs of points. So, we can start the proof by saying, axiom 4p point 2 implies that there are at least, we count the number of pairs, so that would be a combination of 4 taken 2, which is equal to 6 lines in the 4-point geometry. So we have shown the existence of at least at least 6 lines. Okay, that is based on axiom 4p.2. But then the theorem, again, take note that the theorem asserts exactly 6 lines, meaning the lines should be at least and at most 6 at the same time. So we now have to prove that there can be no other line except the 6 lines that we have named or considered. So we can assume that, suppose that there is a 7th line, but then by the way, we have used the number 4 here. This is the number of points. Therefore, this is not only based on axiom 4p.1, but also axiom 4p.2, but also based on axiom 4p.1. So we say axiom 4p.1 and 4p.2 imply that there are at least 6 lines in the 4-point geometry. But if we assume that there is a 7th line, by axiom 4p.3, this line, axiom 4p.3, such line must contain exactly 2 points. But in our first argument, every pair of points has been accounted for. Because when we count the number of combinations, we have considered all possibilities of 2 points pairing among the 4 points given. Meaning, this means that the 7th line, or that this line, is one of the 6 lines mentioned. Therefore, there can be no other line except the 6. Hence, we can say that there are exactly 6 lines in the 4-point geometry. And we're done. Okay? So if you have some questions of the proof, about this proof, you can ask me through our group chat. Okay, so let us go back to our module. Okay, so upon reading those pages assigned to you, you should now keep in mind that the 3 properties discussed, the consistency, independence, and completeness, are 3 different properties. Not 1, implies any of the other two. Hence, the verification of each should be independent from the verification of the rest. But again, in verifying completeness, it would suffice to show that any two models are isomorphic. Let us now consider another example. So we have here axioms for the 3-point geometry. So this is another finite geometry wherein there are exactly 3 points. So here are the axioms. There are 4 axioms in the 3-point geometry. First axiom, there exist exactly 3 points. Second, 2 distinct points are on exactly one line. Then not all points are on the same line. And fourth, 2 distinct lines are on at least one common point. So we are asked here to prove that the system is consistent. Then the system is independent. Then to prove the theorem that 2 distinct lines are on exactly one point. Actually, the solutions are there. Okay, so first we have to show that it is consistent. So we simply have to make a model wherein all 4 axioms are true. So again, there are exactly 3 points. So we have the points A, B, C. Then 2 distinct points are on exactly one line, meaning each pair should be on exactly one column. What are the pairs? A, B, or in this case rows. The lines are the rows. So A, B, A, C, and B, C. So axiom 2 is true. Axiom 3, not all points are on the same line. There is no line containing all 3 points A, B, and C. So axiom 3 is true. Then next, 2 distinct lines are on at least, or 2 distinct lines are on at least one common point, meaning 2 lines should have at least one point in common or an intersection. If we are to name all pairs of lines, we have A, B, and AC. Intersect at A, AB and BC intersect at B, AC and BC intersect at C. There is no other possible pair of lines. So we have considered all pairs of lines and each pair has an intersection, therefore axiom 4 is true. So this is a model which shows that the system, the 3-point geometry is consistent. Now, for models demonstrating independence of each axiom. Here is the independence of the first axiom. So consider a system with 4 points, A, B, C, and D. And then the lines A, B, C, AD, BD, and CD. So let us examine this. First axiom is already false because there are already 4 points. Second axiom, which states that 2 distinct points are on exactly one line, meaning all pairs should be, or each pair should be in exactly one row. AB is in ABC, AC is also in ABC, AD is in AD, BC is in ABC, BD is in BD, then CD is in the line CD, meaning each pair of points is contained exactly, or is contained in exactly one of the lines, meaning axiom 2 is true. Then, not all points are on the same line. There is no line containing A, B, C, and D in one line. Therefore, axiom 3 is true. Second, the fourth axiom. 2 distinct lines are on at least one common point, meaning each pair of lines intersect. A, B, C, and AD intersect at A. A, B, C, and BD intersect at B. A, B, C, and CD intersect at C. Now for the pairs containing AD. AD and BD intersect at B. AD and CD intersect at D. And lastly, we have BD and CD intersect at D. Meaning, there is no pair which has no common point. Each pair of lines has at least one common point, which satisfies the fourth axiom. So, here, only axiom 1, axiom 3p.1 was not satisfied. Therefore, axiom 3p.1 is independent of the other three. Here we have an axiom showing the independence of axiom 3p.3. So we have the points A, B, and C, the lines A, B, and B, C. Let us examine this model with respect to the axioms. First axiom is satisfied because there are exactly 3 points. Second axiom, which states that two distinct points are on exactly one line. Two distinct points are on exactly one line. What are the two distinct points? A, B. AB and BC, but there is no line containing AC. So, this does not satisfy axiom axiom 3p.2. Okay, axiom 3p.2 is not true in this model. Axiom 3p.1 is true. Axiom 3p.3, which states that not all points are on the same line, is true here because there is no line ABC. And then, every two lines intersect is what we meant by axiom 3p.4, which is satisfied because there are only two lines and they intersect at B, meaning only the second axiom was not true. Hence, we can say that axiom 3p.2 is independent. Next, here we have the model demonstrating the independence of axiom 3p.3. Here we have the lines A, B, and the points A, B, and C, and there is only one line ABC. Clearly, axiom 3p.1 is satisfied. And then axiom 3p.2, which states that every pair is on one line. We can only have one line. We have only one line, meaning each pair is present, AB, AC, BC, contained in one line, meaning the second axiom is satisfied. But the third axiom clearly is not satisfied because all points are on a single line. And then axiom 3p.4 by default is satisfied because axiom 3p.4 applies only if there are more than one line. Because if there are more than one line, we would have to look for an intersection. But there is only one line. So we say that axiom 3p.4 is not violated, meaning it is satisfied by default. Therefore, only 3p.3 is not satisfied by this model. Therefore, axiom 3p.3 is independent of the other three axioms. Lastly, we have, in this model, we have three points, A, B, and C. The lines are A, B, A, C, B, C, and A. So, examine the four axioms. Axiom 1 is true because there are 3 points. Axiom 2, which states that each pair should be in exactly one line. So we have AB, AC, BC are the only pair, and they are in exactly one line. There is no other line containing AB. Is there? There's no other line containing AC. There's no other line containing BC, and these are the only pairs possible in these 3 points. And then the third, stating that there is no line containing all points. There is no line ABC here. Okay. But then, axiom 3p.4 is not satisfied because if we would examine the lines BC and A, BC and A do not intersect. They do not have a point in common. Meaning the fourth axiom is not satisfied even if the first 3 are all satisfied. Meaning the fourth axiom of the 4-point geometry is true. Since we have proven that all 4 axioms are true, then we say that the system is independent. Next, we have a theorem stating that 2 distinct lines are on exactly 1 point. So by axiom 4, it would suffice to show that it is not possible for 2 lines to be on more than 1 point. 2 lines are on exactly 1 point, meaning there can only be 1 intersection. So suppose there are 2 lines, L sub 1 and L sub 2. And they meet or they intersect at 2 points, A and B. By axiom 3P.2, 3P.2 states that each pair is in exactly 1 line. There can only be 1 line that can contain both A and B. But in this assumption, we have 2 lines that contain A and B. This would contradict the assumption. Hence, by proof by contradiction, this would lead to our conclusion that 2 lines can intersect on exactly 1 point. Why? Because again, by 3P.4, it is already stated that there should be an intersection, at least 1. Okay? So there is at least 1, but there can be not more than 1 by this argument here. Therefore, there can only be exactly 1 point of intersection. Okay? So that's it. It's now time for you to do your part. You have there the learning task. Okay? Please write your answers on sheets of paper, then have it, or you can have it encoded, and then pass a Word file or have it handwritten, take a clear picture, and then send it through through my personal messenger. Let me first clarify this. When we say dual of a statement, we simply obtain the dual by simply interchanging points and lines. Okay? So for example, the dual of this, we have here the word line, there is the word point. If we change this line by points and this point by line, the statement would be 2 distinct points are on exactly 1 line. So that would be the dual of this statement. Okay, so that is what we meant by dual. So for you, for your learning task, please go back to the statements of the 4-point geometry and then make the axioms of the 4-line geometry by dualizing the axioms of the 4-point geometry. Next, you would have to verify the consistency and independence of the 4-line geometry in the same manner that we have proven the consistency and independence of the 4-point geometry. That would be all for now. Okay? Again, if you have some questions, you can ask me through our group chat. Thank you for listening.